Okay, so we started off with an algorithm called as artificial potential field. Reactive algorithm looks at everything around and does lead to the robot going to the goal. But imagine a general scenario like I've got a pretty narrow corridor and with a potential field minus oscillation traveling inside the corridor is okay, that's possible. But I've got this kind of a map where it's indispensable to enter the corridor, and the robot is pretty big, so it just fits in. And as it travels around, what will happen is that it'll get reasonable repulsion from both the corners. It has to come very close to the obstacle corners to enter the corridor. That the repulsion is gonna sufficiently cancel out the attraction to goal, and that's a big problem. Robot will not even enter the corridor. Um, we pretty much solved this thing up in an algorithm called as velocity obstacle. Of course, it could not handle static obstacles like that, but it relied upon what is the geometry. So most of the formulas were like the coordinate geometry classes, where we'll say that, okay, this is the environment, it's this obstacle, so I need to avoid from this side, this obstacle, I need to avoid from this side, I can clearly see there's path inside it, so let's just enter. Now, and it can solve pretty much interesting problems. It can, based on geometry, I can say that this is a corridor, it has to be entered, so I will enter the corridor. I won't be bugged off by the repulsion from the corners of the door, and it makes entering the obstacle or corners possible. But then what it doesn't do is that it doesn't account for uncertainties. So I'm not really sure of whether there's an obstacle around or not. I can see something pale. It can be an obstacle or it can be just an illusion. With the robot, especially, the sensors cause this false positives for obstacles that you're not sure of. So you need to decide. And in case of potential field, what would happen is that depending upon the location, it will cause some minor repulsion. The robot is not going to be very bothered about it until it gets to very close to the obstacle. And once it gets very close to the obstacle, then the false positives is a rarity. Geometry can completely mess up if I am not sure about whether something is an obstacle or not. It's just not a term which gets added to a straight mathematical formula. It's more than that. It decides where I enter, where I don't enter. The obstacles have a geometric meaning. So now what we're going to do is we are towards taking the pros and cons of both, where the potential field handles uncertainties very well, but it cannot enter corridors because it has no geometric information about it, and geometry, which captures all the corridors and places where I have to enter no matter how congested, very well. But then the problem is that uncertainties make it very difficult for me to understand what's going on, whether I can enter or not. The new algorithm is called as a vector field histogram. So let's define the problem. For now, I take the robot as something which is point. I will now take in static obstacles, and I won't be considering the speeds of the obstacles. So dynamic obstacles become exactly same as static obstacles. No longer are the speeds considered. Any shape, I will be considering a goal as well. So now what I'm going to do is that in every algorithm, only the nearest obstacles concern me, and the obstacles like these which are far off do not consider me. So I assume that my decision making is restricted to this window of size W cross W with the robot right at the center at W by 2 and W by 2. So that's my local decision making. And what I'm going to do is that I have a grid map of size m cross n. So in this grid map of size m cross n, x of ij denotes whether there is obstacle at location I comma j. Now, I said uncertainties, that was the mantra. So I also have things like this. So it doesn't appear to be an obstacle, there's no obstacle around, but it may be an obstacle, and something like this. So I've got some uncertain regions around as well. So instead of xij, I take cij as the certainty that there is an obstacle at location I comma j. Now, if Cij is say 0, that means Ij is guaranteed to be free. If Cij is equal to 1, it means Ij is obstacle. And in all other cases, it denotes the probability of something being an obstacle or not. Now, in order to understand why is this specific modeling used, we need to understand practical real robots. So, the robots have something which are called as sensors, and common sensors are the proximity sensor. So the proximity sensor is something like a laser on the center of the robot, and what it does is that it sends a laser beam, it strikes an obstacle and gets back. So it reports that this definitely is an obstacle and all these areas are free, and similarly the beam goes all around. It can also have a stereo camera. So the stereo camera looks at this thing, it says it's an obstacle, and because it's stereo, it also gets the depth at every point. So every obstacle that I sense, I can map it into a plain canvas of m cross n size, and I can get a beautiful black and white picture, which is my old modeling. And that's the one that is used most of the times. You take an empty canvas, let the lasers hit obstacles, come back, plot that point as an obstacle in the map, let your stereo camera look at an obstacle, do the triangulation depth analysis, plot that point as a obstacle, let your sonar sensors detect obstacle, plot it as a black mark on this canvas. So I start with an obstacle-free white canvas, and as my sensors invoke something, I keep on putting black dots. That's my Xij. But then practically what happens is that the robot is moving. And because it's moving, sometimes the robot does weird things with us. So the point 5,5, which was earlier reported to be an obstacle, is now suddenly not an obstacle. The moment you take two readings, both the readings don't agree, there's a problem. So the robot took the first reading when it was at the origin, it moved 1 meter, it took another reading. After doing all the transformation global so that my map is at a global level, not with respect to the robot, the same point becomes a non-obstacle. It's very common. I get 3 readings, all 3 do not agree. So what I do is, instead of this, I store this. What I store is, I store log likelihood. So sometimes sensors say this is an obstacle. I increase my confidence of the point 5 comma 3 being an obstacle. Sometimes they say it's not an obstacle. I increase my evidence for not being an obstacle. And depending upon the both of them, I calculate the log likelihood or I calculate the probability that something is an obstacle or not. In general, the robot moved for 2 minutes. 100 times it said it belongs to an obstacle, 950 times it said it does not belong to an obstacle. So the certainty factor over here is 100 divided by 950 plus 100, 100 divided by 1050. And that's practical robots. The robot will keep getting confused whether a point is an obstacle or not. So practically when the robots move around, this is most practically what we get by continuously getting information whether a point is obstacle or not obstacle. So I store it as a confidence map or I store it as a certainty map. So what we're going to do is we are just going to apply a potential field in this grid map, and now because this is a grid map, I discretize it up. In potential field, we mostly assume that it is continuous, and now it's a grid map of size W cross W. And it's not beautiful black and white picture as it is something else. So let's take any general X, O, Y, O. It may be an obstacle or it may not be an obstacle. So C X0, Y0 is the confidence that this is an obstacle or not, and I'm going to use the same repulsive force formula. So the repulsive force applied due to an obstacle O, and I only consider its magnitude, not the direction. So earlier it was 1 upon distance between X, O, Y, O to the center of the robot, the whole cube, and I said that it becomes unstable because the moment you start approaching 0, it suddenly shoots off, and that's what I said it is, that it hits small, 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 and then suddenly it becomes infinity, and that irritates me. So previously I took an exponential, this time I'll take a linear. So distance between x0, y0 and xr, yr, where this is xr, yr. Robot's position, and it's minus, so it's additive, it needs to be positive, so I say it's A and the proportionality constant B. So there are two ways you can inverse. One that was done with potential P field, 1 upon something, and of course you can put a minus sign that also becomes inverse, and then I need to account for certainty, so I say certainty of the certainty of XO, YO, and let's take the square of it for no reason. So that's my magnitude of the force, and my direction of the force is theta O is A tan 2 Y0 minus YR X0 minus XR. That's the direction of the force. That's the slope of the line. So this is theta 0. So it's doing exactly the same thing as a potential field, and I've calculated the repulsion force, and I could pretty much add it as vectors around over here, exactly the same that we had done with potential field. First, let's look at these constants, and can we give them a better representation? Now, I know that this force is largest over here at a distance of 0. So the largest that this term can get is when d becomes 0, when it's A. So I say A is equal to F max, which is the maximum magnitude of the force. And I know that at this point, the force should become 0 because after W, I'm taking everything at 0. So at this thing, it should also become 0. So the maximum distance possible is, so this is W from left to right, so this is W by 2, and I've taken a window of W cross W. The distance will be from here 0, 1, 2, 3, 4. So it's from 0, 1, 2, 3, 4. That means it will reach W minus 1 by 2. And then I need to measure the diagonal distance. So this is D max. So into root 2. So if I put this distance over here, it should become 0, which means A minus B times D max W minus 1 by 2 root 2 should be equal to 0. A is already F max, should be equal to B times W minus 1 by 2 root 2. That means B should be equal to F max root 2 divided by W minus 1. So these are intuitively easy to set.